I would like first to thank Stéphane Védry for inviting me. Stéphane is a former colleague from the University of Montpellier in France. And also I would like to thank also all the organizing committee. So I will give you a few words about how innovation in food packaging can help fighting plastic pollution. Okay, here is the first slide. So we know all that food packaging is a key actor of food consumption, and this is a very important element of processing, storage, transport, marketing, and also consumption between the field and the plates. But now we know also that there is another step that is a little bit less positive. This is after usage step, up to waste management, and up also to final, as we will see a little bit later, as up to the final fate of the materials. So now we all are facing the issue of balancing the positive impact of packaging materials for reducing food waste and losses, and on the other hand, the negative part, the negative impact of packaging materials, and especially in our environment. And this is really one of the main issues we are currently facing, and this is also one of the reasons why the previous speaker, Caroline Locke, has just presented us these materials, which are bringing new benefits for the environment. So maybe let this the food packaging as 3 case steps on its life cycle. And if the benefit is mainly during the usage through its functional property, which of course should be adapted to the food preservation, the negative impact are mainly during the production of this packaging and of course after the usage of this packaging materials. And we know that plastic packaging are bringing some very specific issues which are linked to the fact that these materials plastic materials have a very specific behavior that is very different from all the other materials humans have used up to now. They are not able to slowly solubilize like metal or glasses, for example, to remineralize water and soil. They are not able to biodegrade like all organic matters in order to reintegrate the carbon cycles. They have a very, very specific behavior, and plastic materials are able to fragment, to persist a very long time, because this fragmentation take a very long time. They're able to diffuse, and once they've reached the micrometric size, they can diffuse everywhere in the compartments, the environmental compartments. And once they reach the nanometric size, they are able to translocate, which means to diffuse inside, to pass through the barrier of our organs, and to diffuse inside the organs of living beings. And the results is that usually it means that life cycle environments are systematically and unfairly underestimated the environmental impact of plastic, and therefore favor plastic compared to all the other materials, whether they are papers, metal, glass, and so on. So in our laboratory, we have decided to set up a strategy to develop new materials, what we call innovative materials, that are not presenting the issue of fine particle pollution. So the objective is really to develop materials that are fully biodegradable in natural condition at the very end, which means that they are presenting zero risk in terms of particulate plastic pollution, fine particles pollution of plastic waste. And we have also decided to work only on non-food raw materials in order to not compete with food usage. And for that, we have used agricultural residues as raw materials for the production of polyhydroxyalkanoate. In fact, this is PHBV, butyric valerate, as a biosourced materials, but non-food sourced, which is bioprocessed. It is fully biodegradable and it can be biorecyclable. For the time being, we are really working on the making this PHA material, PHA-based materials, more resistant for being able to be reused and recycled also via mechanical recycling process. Okay, so this is the this is according to the Plastic Europe figure. In Europe, you can see that there is about 1/3 of our plastic packaging wastes that are incinerated, 16% landfilled, 13% non-collected. There is only a few percent that are closed loop recycled, and then the rest that is called recycles, in fact, they are either downcycled or exported. So at the end, if we look at the fate of our materials, this is more than 61% in Europe of our plastic packaging waste that are ending in our environments and are increasing our reservoir of micro and nanoparticles. And our objective is really to increase this part of biosourced and biodegradable and biorecyclable also materials, to increase this green here, this green arrow of materials. So here it is. This is an example of materials we have developed. We used agricultural residues. On one side, we are using liquid effluent like cheese whey or water from oil washing and different type of agricultural residues as a fermentation substrate for the production of PHBV. And on the other hand, we are using solid wastes like wheat straw, vine shoots, and so on, that are going round, and in order to produce lignocellulosic fiber-based fillers. Both are compounded together, and the structure is tailored in order to obtain the required mass transfer properties, which means water vapor barrier properties, oxygen properties, but also carbon dioxide properties adapted to the food preservation. Because for each food is requiring very specific properties, and having the highest barrier possible is not the good solution for food. And the result is that we are currently using plastic barrier films that have too high barrier, and we are micro or micro perforating them. So each materials need to be adapted to the requirements of the food in order to increase the shelf life of the food and reduce food loss significantly. And then the materials obtained here, we have an example of these trays, are fully compostable in natural conditions. which means that you can put it in your garden and the material will fully disappear in a few months in order to reintegrate the natural carbon cycles. For the production of this PHA, we have developed a combined process coupling two-step anaerobic digestion for the production of biogas and digestate. And this two-step anaerobic digestion is also producing, in addition to biogas and digestate, VFA, volatile fatty acid residues. And these volatile fatty acid residues is used for the PHA production. And this here, you can see the pilot plant that we have developed in Verona, in Italy. This is the Innoven companies. This has been also financed by the company, but also, of course, in the framework of a bigger project, which is a European project. And this, by coupling this production of PHA with biogas and digestate, it means that we are able to increase the added value of all the agricultural residues, okay, and also to facilitate the development of such type of process also at local scale. These PHA are mixed with lignocellulosic fibers in order to decrease the economical cost, but also the environmental cost of our trays, and to tailor also the barrier properties, the permeability, I would say, of our trays according to the type of food we are intending to pack with. And the mixtures of PHA and lignocellulosic fibers are shaped with commonly used thermoforming processes, industrial thermoforming processing. In fact, this is injection molding simply. In some cases, we are using some specific additives to give some additional active and intelligent function to our materials. Here, this is an example of oxygen absorbing additives we have developed based on synthesizing nano iron on nanoclays, and the additive is then dispersed within the material itself during the shaping process, and there is a very efficient absorption of oxygen and therefore an increase of the barrier properties of the materials when necessary, of course, only. Currently, we have produced these materials at the I would say pre-industrial scales in different type, in different shape. We have tested also these packaging materials on different food with fresh fruit and vegetables. Of course, it was the easiest, but also with fresh cheese actually, fresh meat, and also fresh poultry. These materials have been developed in the framework on 4 different European projects. The first one was EcoBiocap. He handed about 5 years ago. The second one is the NOAA project, which means no agricultural waste. This is in this particular European project we have developed the coupled process with anaerobic digestion of PHA production with anaerobic digestion. We have also made some scientific and technical advances in the razor-based project, which was not coordinated by INRAE, but by the University of Roma. And here we have made some advances in order to use other residues than agricultural residues for the production of these materials, and especially by using urban residues, both for the as effluent for the PHA production, but also for the production of lignocellulosic fibers. And we are also currently going on developing this material, especially by adding some intelligent and active function in the framework of the GLOPAC project, which is also a European project. And all these materials have been developed using multiscale approach, where there is 3 main scale which are used. The first one is the material engineering scale, where we are studying the material itself at the different scale, molecular, nano, micro, and macro. The second scale is dealing with mainly with the food packaging system. They are mainly including process engineering modeling, which means that here we are considering the packaging with the food itself and how this packaging is able to answer the requirement of the food in terms of barrier properties, active, for example, antimicrobial properties, and so on. And the third scale is the scale of the stakeholders themselves, where we are taking into account the industry's requirement, the consumers and end user requirements, but also environmental aspects. And here we are developing what we call knowledge engineering modeling. And all these scale are coupled. This is an example of what we have developed, a multi-scale structure mass transfer prediction systems, where we are developing modified atmosphere packaging according to the different type of packaging extra, a simulation of modified atmosphere packaging with the food itself, and then a multi-criteria querying able to when associated to packaging database to be able to rank packaging solution according to the requirement of the different stakeholder, which means that you will say, for example, I want a material with this permeability of oxygen, this permeability of water, vapor permeability, but I want a cost lower than X euro per kilogram. I want a transparent or not a transparent, and so on. And currently we are using this tool, this decision support tool, for eco-designing our materials, and we are also working on translating all the output of this decision support system into more comprehensive environmental impact. And this is an example of environmental score, global score we have developed, that is taking into account the raw material origin, the food losses reduction, so its efficiency and its necessity to reduce food loss. And the third parameter is about the material end of life. And for each parameters, there is a score which is indicated according, for example, if the material is renewable, not renewable, from competing with food, and so on, and etc. Okay. And that's all. Thank you for your attention.